Q&A at the end of the presentation. So I'm going to now turn it over to our first speaker, Suman from IIT BBS.
Yes, ma'am. Shall I share my screen?
Yeah, if you feel comfortable, you can share it. If that doesn't work, then I can do it.
Is it visible, ma'am?
It is. You're on slide 3. Yes. So if you want to go to slide 1 and get started, that'd be great. And do full screen. Perfect.
Shall I start, ma'am?
Yeah, go ahead.
Myself, Suman Biswal, research scholar of IIT Bhubaneswar. So my topic for today's presentation, it is under theme 4, microgrid and active distribution system, development of optimal protection coordination scheme for microgrids. So basically the introduction to microgrids, as per the definition from Department of Energy, microgrid is defined as a group of interconnected loads, distributed energy resources, which clearly define electrical boundaries that act as a single controllable entity with respect to grid and can connect and disconnect from grid to enable it to operate in both grid connected or island modes. So the integration of distributed generation gave birth the concepts of small scale power system or independent power system can be termed as microgrids. Microgrids have numerous advantages, including that it can support power demand located in remote areas, for example, hilly or any isolated islands where the cost incurred due to transmission and distributions are high. So naturally the challenges came up after the integration of distributed generation. So some of them are listed here. The first one is low inertial system, because in microgrids we have distributed generations and they're basically inverter based. So so unlike conventional system, the best generation, so they have very low inertia. So when there is any disturbance, so it alters the or it disturbs the voltage frequency. That brings challenges to the utility to maintain the power quality, and also stability and reliability challenges are there in microgrids. And to support the load demand, we need storage, including batteries or supercapacitor, and also some advanced sensors and control technologies should be there. And islanding and resynchronization is problematic, and obviously the microgrid protection is a big challenging. So as per protection perspective, so some of the challenges or the major challenges are highlighted here. That is bidirectional fault current. This is due to the fact that when DGs are integrated, so DGs start contributing towards the fault location. So the direction of fault current changes. So this necessitates the the incorporation of directional relay in the lines, which increases the cost of the system. And the second one is protection blinding. This comes because since DGs we are integrating at various locations, or as we can say at various buses of distribution system, it reduces the current drawn from the substation reduces. So naturally the relays which are located upstream or upstream to the feeder, the current sensed by that relays reduces. So it may happen that the relay locating in upstream position didn't see didn't find the current as faulty current as such. So in that case, it remains blind to that fault. So this type of problem arises, that is protection blinding. And also fault level. So fault level increases. This happens when suppose we have a distribution where we have a networks or microgrids. So and suppose one DG is placed at some bus. So whatever the downstream to the DGs, the fault level will be increased because of DG penetration. So naturally the circuit breaker capacity needs to be modified or changed because of DG penetration. So another thing is sympathetic tripping. So this is also arising because for this, let us consider an example. We have a 2 feeder, and in one feeder, DGs are located. So suppose one fault happens in the adjacent feeder, so that DGs contributes fault to that adjacent feeder. So it may happen that a DG exceeds the current. The setting of the relay located nearest to the DG it may exceed the setting of that particular relay, so it will unnecessarily trip the unfaulted line. So this is called sympathetic tripping. And also miscoordination of relays. So relay, particular settings, especially time multiplier setting or plug setting, will not, cover all the network topologies. So for example, microgrids can operate in grid connected or islanded, and also there may be many contingency issues as well. Okay, for example, line outage or DG outage. So this may happen. So this may, so for a particular or a single setting will not take care the protection issue. So this miscoordination of relays happens due to that means the integration of DGs, or in microgrid these challenges comes up. And unintentional islanding of DGs is also happens because the faulty under faulty situation, the DG may completely isolate if it exceeds the pickup setting of that relay nearest to it. So unintentional islanding of DGs is also one of the major challenges in microgrids. So our objective is to provide optimal settings of the relay, and we will here we are proposing non-standard tripping characteristics. That is, not standard. We'll see the standard characteristics as well, but here we are proposing user-defined or non-standard tripping characteristics to provide protection for various modes of microgrid operation. As we have discussed, that the particular settings will not take care the all other network topologies. So the settings needs to be modified on based on the scenario. And also we'll test the system on microgrid one test bench, that is on IEC 61850, and later we'll see the validation procedure on RTDS simulator. Actually, currently the validation is going on. It's not fulfilled the third objective, but I'm currently doing this the third objective. Then our proposed problem of the relay coordination problem or the protection coordination problem can be formulated as an optimization problem. Here we have stated we are going to minimize the summation of all the operating times of primary and backup relay. For example, here we have the first term in the bracket. So this is a primary relay. So this so TFLI, this is the fault at location I with subscript P, that is primary relay. So for each primary relay, we have one or many backups. So we have to take care all the primary backup relay combination and also the various fault location. So this is our objective function that we are going to minimize. So to ensure the coordination of the relays, and this time of operation is written, can be expressed as in equation 2. So that is beta TMS the whole divided by PSM to the power alpha minus 1. So beta and alpha that governs the characteristics of the relay. So for example, for beta equals to 0.14, alpha equals to 0.02, that gives us the inverse characteristics of the relay. So that will be the normal inverse. So if beta and alpha changes, so the characteristics will change. So for very inverse or extreme inverse, the other characteristics are there. For them, the beta and alpha varies. Change. It's to be changed. So here we propose to, instead of taking the fixed values of beta and alpha, we consider the variable beta and alpha in the relay characteristics in the relay characteristics modeling. And this PSM can be written in terms of fault current divided by plug setting into CT ratio. And so the objective function stated in the earlier slide needs to be minimized subject to these constraints. The first constraint is the coordination time interval criteria, which says that for any fault at a certain location, if the primary relay fails to operate, then the backup relay should operate after certain time interval criteria, that is we called CTI or coordination time interval. So here TB, that is a backup relay for fault at location FL minus a fault at the same location for sensed by the primary relay must be greater than equals to the CTI. So this coordination interval criteria must satisfy. And the second constraint is the operational time of the relays. So the operational time of a primary relay must be assigned. Some timing, that is we have assigned here 100 milliseconds as per the standard value. That is that means it should take minimum 100 milliseconds time. For operation. For example, so if primary relay takes 0.1 second to operate ideally, then the backup relay will operate 0.4 seconds. So we are here, and here we have taken 0.3 seconds as a coordination time interval criteria. And also the limits on the time multiply settings. So TMS, that is also one controllable parameter for relay. So that is also represented in form of bounds. Similarly, the pickup settings or the pickup current is represented in the inequality form. And this is the constant phi. This is a constant relay constant. So here we are considering the variable beta for the protection of microgrids. And so finally, what we are getting is our final objective function becomes considering all the constraints. This second term is added so that if any constraints is violated, then at least one constraint if it violated, then we will add or we will add a very large penalty so that the corresponding solution or the corresponding, here our solution vector represents the relay parameters, that is TMS, plug settings, beta, alpha. If any doesn't satisfy, then we will add a large penalty so that that particular solution removes out of the solution space. So in this way, we have formulated the objective function, and the parameters of the various relay parameters are here listed out here. For example, coordination time interval 0.3, primary relay operational time 0.1 second or 100 milliseconds. We have explained, and then we have a time multiplier settings bounds and also the pickup current constraints. So we have taken the pickup current as 1.25 times IL max because this pickup current is decided on the basis of the normal load current. So whatever may be the normal current flowing related current. So based on that, we have multiplied with a factor 1.25. So this gives us the pickup setting value for our case. And also the bounds on the relay constants are also specified. And this is our proposed scheme. So basically what we are doing here, we are the optimization parts that will calculate all the relay settings for all the topologies. The topology which are very essential. So all the topologies needs to be for that set topologies, the settings needs to be calculated. So the algorithm starts here. As you can see, we have an online unit and offline unit. So offline, so all the optimization, optimization part will be included in the offline part. And in this case, it will, for example, it will read the system configuration, whether it's a grid connected or islanded mode or any other configuration. So based on that, it will decide the primary backup relays. Then based on the short circuit studies, the relay will be, the settings will be calculated, and we will store in the relay settings. So basically, in a numerical relay, we have the provision for relay for storing the setting group. I have seen 6 setting group for ACL 451 relay, so that can cover at least 24 topologies. 6 setting group, and each setting group can take care four settings, 4 subsettings. So if there is any change, so the online part will be, if there is any change in the network, it will detect, and if the coordination, all these things hold, then it will maintain the settings. Otherwise, the settings needs to be updated. So this is our proposed idea of implementing the coordination scheme. And here we have implemented the optimization technique, that is chaotic cuckoo search. That is a modification over the original cuckoo search algorithm. So like other algorithm, it is the initial solutions are generated within the bounds. Here for NH is the number of host nets or population size. So like other algorithm, the initial solutions are generated within the bounds. And this RAND is uniformly distributed random numbers. It's mentioned from 0 to 1. So all the variables, or in our case, for example, plug settings, TMS, all the variables are generated within the bounds as per the hostness number or the population size. So at first we will make this. Then the solutions are updated based on this equation 13 and 14. So in original cuckoo search algorithm, the step size or step length is fixed. So we propose that instead of taking the fixed step length, we take the variable step length using the chaotic sequence based on the logistic mapping. So this is the equation to implement the logistic mapping, that is tau at j plus 1th iteration equals to mu tau j 1 minus tau j, where mu is the chaotic attractor whose value is assigned to 4 as per the this chaotic sequence the value that is specified, that is mu is 4, it is given. and there is some limitation that it will not work for to some particular values. For example, 0, this chaotic sequence will not work on 0.25, 0.5 on all these situations. So we vary, instead of taking the fixed step value, we vary the step length in using chaotic sequence based on the logistic mapping. So this is the nature of the chaotic sequence. So instead of taking the fixed, so this is the variation. And also instead of, like in the previous slide I showed, this tau j would vary from 0 to 1. So instead of varying from 0 to 1, we restricted the variation from 0. It was found by trial and error that it is from 0.01 to 0.5. The chaotic sequence give the optimum performance of the the optimization technique. So here these are some parameters specified. So for case study 1, here case study 1 is our the normal normal distribution system, that is without any DGs, or our conventional distribution system is categorized as a case study 1, and case study 2 is our the distribution system or microgrids equipped with DGs, solar and wind based, and various control parameters are specified. For example, nest discard probability, distribution factor, all these are the parameters of the chaotic cuckoo search algorithm. And this host nests or iteration number, which is same for other algorithm, or this is population size or iteration number. And similarly for the last case study 3, only the iteration number is changed to 2500, and this case study 3 belongs to the islanding mode, or autonomous mode of microgrid operation. Here we have considered only three cases: islanding, grid connected, and the conventional mode of operating the distribution system. And this is our test bench. That is, here we have 5 lines. So faults are conducted here in each lines. Then here we have considered the 3-phase fault, balance fault in the middle of the line. Since it is in microgrid, it is assumed that the lines are short. So the fault at the midpoint is made, and because there will be not any appreciable change in the current, so that's by taking that assumption, we conducted or we introduced the fault at the middle of the line, and here at various buses, the inverter based DGs are installed. For example, at bus 2, we have introduced the wind based, and bus 4 and bus 6 are the solar based DG, and these circuit breaker switch are in closed condition. It can be there is a provision to make it radially operation, to make it operate as a radial. So here in our cases we have considered the circuit breaker switches are in closed condition, and these are some of the data. The ratings specified. This is taken from this literature 4 and specified over here, and the distribution lines we have modeled as a pi network, and these values are specified. And after that, we got the settings for the 3 case studies, that is C1, C2, C3. That is C1 is your not a normal conventional way of operating the distribution system, and C2 is our distribution or microgrids connected with the DGs, all the DGs, and C3 is islanding mode. So in all the case studies, at all the false points, the primary and backup relays are decided, and the optimal settings are calculated, and the operational times are also calculated. So for example, if we observe any data, for example, for fault at location F3, the C1 operating mode will give the operating time as 0.61 seconds, and the backup relay will give the 0.863 seconds. Okay, so the difference between these two is 0.3 seconds, more than 0.3 seconds, at which ensures the coordination time interval criteria. That is, we have assumed 0.3 seconds. So in this way, the settings are calculated. Similarly, it's also tested on a small system, 3-bus system. It is taken from this literature where genetic algorithm, another optimization technique is used. So it has found that the proposed CCS is capable of generating better solution, and it is found that the total the objective function value is 11.874, whereas the GA technique provides this 15.17. And these are the convergent characteristics of the objective function, and it's compared with the original cuckoo search. And here we have considered only the up to this we have considered the standard operating characteristic of the relay, that is beta is 0.14 constant and alpha is 0.02. So and we have compared that, and yes, the chaotic cuckoo search gives improved solution compared to the original cuckoo search algorithm, and the converging characteristics are also better. So these are the first one is case study 1, that is the conventional way of operating this distribution system. Second one is a grid connected system with DGs, and third one is islanding mode with DGs, and here fourth one is that is a 3-bus system. Here also we found that CCS is superior to CS algorithm. And now we consider the UDRC scheme, or the non-standard tripping characteristics, where we varied the beta and alpha, and we have found that when we control more parameters of the relay, the better solutions are obtained, and also better coordination criteria. So here we have seen that the operating time is also improved for all the 10 relays, because we have 5 lines, and each line we have 2 relays. So here, better performance is noticed for UDRC scheme. Similarly, for the second case study, it also gives us better results. Third, that is the islanding mode. Similarly, the beta and alpha is also taken as variable. It gives better results. Compared this standard relay characteristic with UDRC, so it is seen that if we observe this third and fourth column, so the primary operating time is 0.4. So better operating time is obtained in case of UDRC scheme, as we are controlling the more variables, for more relay parameters. So and in all the cases, the primary relay operational time as a constant is set to 0.1. So in all the cases, the time of operation is more than 0.1 or nearer to 0.1. So better improved performance is obtained, not only in primary relays and backup, ensuring the coordination criteria holds properly as well. And these are the same, the converging characteristics and of the 3 case studies mentioned. So this is grid connected. This case study 2 is grid connected. Case study 3 is islanding, and this is the conventional way of operating the distribution system. And this is a graph showing that if we consider only one setting, then and if we set just for understanding, we made that if suppose this CTI boundary is 0.3 seconds, is a coordination time interval criteria, that is green line, and CTI case 1 is the case 1, that is the distribution system operating without DG, I mean conventional way. So the red line signifies that it's if we follow that setting, then that coordination will hold definitely. But if the same setting is applied to islanding or grid connected mode, the performance gets worsened. As it is seen that for the black curve, that is CTI becomes negative. It signifies that the backup relay operates fast compared to the primary relay. So this is we don't want. So if we change the topology of the system, that the settings of the relay also needs to be changed. Otherwise, the performance of the system will get hampered. So coming back to conclusion, so we have proposed the user-defined characteristics of our microgrid for various modes of microgrid operation, and we change the relay characteristics as a variable control parameters, that is beta and alpha. And here we have proposed the chaotic cuckoo search, that is modified version of cuckoo search algorithm, and we have seen the performance gets better in this with respect to standard characteristic scheme. And also this for the work in progress, I mean the actual system will be modeled in RSCAD software for validation in HIL. So here it is the computer is connected to the RTDS with a Ethernet cable, so communication will be there. And also we have a GTO cards, that is GT analog output. So GT analog, or the real-time voltage and current signal will pass to the voltage and current amplifier, so that the numerical relay gets the proper voltage. For example, if the voltage, if we have seen this is ACL 451, if we exceed the 6 volt peak value, then this relay will get damaged. So there is a necessity of voltage and current amplifier over there. If this voltage and current amplifier is not there, then we need to make some ribbon cable arrangement, so that this device gets, for the sake of safety of the device. So that digital signal from the numerical relay will be again feedback to the digital input or GTDI of the RTDS. Then the corresponding breaker will operate. In this way, the coordination or the HIL validation can also be done for this work. So it's currently I'm doing, it's not completed, and so very soon I will finish it. And the future work includes the concept of network microgrids. So instead of taking one microgrid, we can consider the protection coordination for network microgrid as well. And also, since the number of operating modes increased, so we need to apply some clustering methods, so that whatever the relay setting group available, so it can accommodate that, so that for better operation. So this is a feature one, and these are some of the references.
Great. So we've got time for a couple questions. So can you go back to your future work slide for a second?
Yes, ma'am. Yes.
Oh, sorry, the picture, the work in progress, I guess.
Yes, ma'am.
Yeah.
Yes,
So you're working with the SEL relay. They have on the front, you can also, you don't necessarily need the amplifier. Do you, is there a reason that you're using the voltage and current amplifier?
No, ma'am, actually, it will be very soon, it will be coming. So as a general block diagram I'm showing, but currently I'm not using. So we have a ribbon cable arrangement. We are completely bypassing now at present the voltage and current amplifier, but later it can be introduced for so the ACL relay told us that we cannot provide more than 6 volt peak value to this device for the safety purpose. Otherwise, we can make it the same signal. We can also bypass this. Currently
Okay.
not used. Yes, yes.
All right. Are there any other questions? All right. Well, thank you very much for your presentation, Suman. We appreciate it. If you can put your information in the chat, we'll head to the next talk.
Yes.
My PowerPoint slide off.
Thank you, ma'am. And